kick this off with what does Phil know about quantum computing? And the reason I'm going to do that is because I don't know much, but what I do know is enough to sort of get by in a bar. So if we start there, we're going over to pick up Andy Stanford-Clark, and Andy is one of the research fellows from IBM, lives in the Isle of Wight, funny enough. So Andy will be able to give us a lot more detail, but let me just sort of try and explain the basics. In previous videos, we have covered off what is technology. And one of the things we covered off was hardware, and we talked about CPUs and RAM and all that sort of stuff. And at a lower level than that, computers, for about, well, since they were invented, have largely worked off the back of transmission of electrical signals. So computers basically talk in ones and zeros. Your electricity is on or your electricity is off. And that is the way that things have been going for ages. Computers have got better and better over the last 60 years. The ones and zeros can can move quite quickly now. There's lots of clever ways that the architecture, the hardware architecture, is designed to make it really efficient, but we're sort of reaching the limits of traditional hardware architectures. And so to try and sort of give you an analogy, the way current computers talk to each other or transmit information between one computer and another, or within the computer itself, it's a bit like a chap with Morse code. So if you imagine a chap or a lady with a flashlight, flashing their torch on and off, they can convey a message. And if any of you remember your Morse code from Cub Scouts, SOS is beep, 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 beep. That is the way you transmit Morse code. And in that 2 seconds of beeping noises I made, I managed to portray 3 letters, SOS. Now, that's sort of interesting and that's fine, but clearly you can see there's limits to the amount you can do. And no matter how quickly you press your button on your torch, there's only so fast you can go to transmit information. Now, if you take that as your analogy for current computing, quantum computing is fundamentally different. Instead of communicating in ones and zeros and electrical signals, what it's actually doing is using subatomic particles to give not just 1 and 0, but a whole range of different numbers. And the way I imagine it is, if you think of that chap with Morse code torch standing next to an 8K television, that is a pretty good analogy, I think, because quantum computing is the 8K television. So instead of having one flashing light, you've got millions of pixels on a screen, and you can use that to transmit information, messages really easily. If you can imagine me doing my beep, beep, beep noises for 2 seconds, standing next to a screen that says SOS, you pretty much get that message a lot quicker. And clearly that's a very simplistic way of looking at it, but it's quite a good way of looking at it, I think. And so quantum computing is really clever, and it mucks about with quantum physics. I don't understand it, and I'm hoping Andy can explain it for us, but it gives the opportunity to transmit a lot of data and process a lot of data a lot quicker. And where it's sort of heading is, a lot of the applications we use in current computing are pretty basic in the grand scheme of things. Quantum opens up a whole new world of opportunity. So instead of just having a simple stream of information like we do today, quantum gives you the opportunity to do so many calculations per second that it can model the whole world. It could model the weather of the whole world, and you could do some interesting scenario testing about, if I build a power station in Southampton, what impact is that going to have on Brazil? Because the whole world is mapped in this quantum computer. So you can sort of see the benefit of it and the power and the reason why it's getting people quite excited. Now, with this new hardware architecture, comes a lot of benefits, i.e., hold on, there's a big tug there. There comes a lot of benefits, i.e., you can do lots of more interesting math stuff, but also comes with some risks. Quantum computing and its capabilities will actually change the way we secure things. If you've heard anything about Bitcoin, for instance, or cryptocurrency relies on the fact that you create a unique key, a unique number, and that is the representation of your coin. Now, it takes days and days and days and weeks of thousands of computers all sitting there working out cryptocurrency tokens. Quantum computers can do it like that. Because it's so clever, it's got so good at the maths, it's very powerful. So If quantum becomes a reality, which it pretty much is, then cryptocurrency might have an issue. And similarly, all of our passwords on our computers are encrypted using encryption that relies on it taking too long to work out a password. Quantum computer, like that. And only last week, a Chinese student announced that he'd managed to find a way of using quantum to hack an RSA token, an RSA secured encryption device. So fundamentally, the world is changing now. And as we move into buying IT, we're going to need to think about the impact of quantum on some of those things. Now, all sounds very scary. It's quite a long way off still. And this is my view, but it might be an out-of-date view. And Andy will give us a real sense of what's going on. Basically, the downside of quantum, it takes a lot of energy, and it only actually works at -400 degrees Celsius. So there's only a handful of quantum computers in the world, because of the really, really deep temperatures they need to operate at. You couldn't just run one in your home. So fundamentally, it's a difficult bit of physics to play with, making the temperatures work such that quantum computers can be mass adopted. But for now, certainly the pace at which quantum is changing and the speed at which the hardware is becoming more and more stable and more robust means that I think in 2 to 5 years, we'll have quantum computers pretty readily available that people can use to do all sorts of crazy things, whether it's model the whole world as a digital twin or crack someone's password and break cryptocurrency. Now, that's my current understanding. I don't profess to be an expert in quantum. Andy certainly is. So when we finally get over to the Isle of Wight to pick him up, hopefully he'll do a better job of explaining it and it'll all become very sensible.